Not every slide has this whatever color background. I tried to go Christmassy burgundy. Eat it. It didn't work out. The funny thing is it's 3 different shades depending on which screen you look at. But anyway, moving on. We're going to wrap up. Oh, you're annoying. We're going to wrap up every bond type today. And then we're going to get this giant piece of paper. And smart kids are going to feel even smarter. And the ones that struggle are going to feel even less smart. I don't know. I can say this dumb kids will struggle and feel dumber. It's okay. I don't really mean it that way, but like this is something that clicks for some kids, like boom. And they have no idea why it doesn't go for other people. They're like, it's not even hard. And then there's some kids that are like, I hate that person. This is the hardest thing I've ever done. Just be patient. We'll get you all there. All right, here we go. We didn't actually complete poll. I don't know. Where are we? They usually, there could be a sharing of 1, 2, or 3 pairs of electrons in a covalent bond. So just, it's this word right here. Page 8. All right. So this is not the right order. That wasn't the right slide, but the blank is covalent. So will you tell your partner at least one thing about covalent that's different than ionic? There's one gigantic thing that's different about covalent. Oh, good job. Covalent share electrons. That's the huge, most important difference. Covalent shares, ionic does not share. Okay, so then we had those pictures. They were just these showing you like how fluorine alone, did I even show these yesterday? Fluorine alone, it's missing one here and it's missing one there. So they share. If they share a pair of electrons, you now have an octet on both, even though you really didn't have one on either. They just overlap this valence shell and form a covalent bond. Covalent means valence together. Same thing happens with oxygen, but it needs more, so it shares 2 pair. And we have nitrogen, and it needs even more, so it shares 3 pair. Hold on. There we go. I'm sorry, Jared, for having my mask off for a second. That mask is my most comfortable mask, but I inhale it when I try and talk, so it gets a little bit gaggy. All right. So it's my resting mask for my resting something face. Yeah, moving on. For like the last 2 weeks, someone in the faculty keeps dropping a thing in my mailbox. It's a fig bar, and it says, I figured you needed to have a pickup or something like that. I was like, wow, my ornery face is paying off with free food. Okay, now, today we're going to talk about polar covalent and non-polar covalent. So today, whoops, just briefly, we have, I have no idea why I started with the L. It just happens, all right? Covalent bonds. There are 2 types of them. They are called polar and non-polar. We'll talk about both. Polar essentially means 2-sided, and non-polar means not 2-sided. All right? So as you kind of think think about like the North and the South Pole on our planet. A polar bond has a plus and a minus half. We'll talk about. Okay, so first is polar. So no 2 elements have exactly the same electronegativity. Now, unless there's that little star, unless they are the same element, like bromine and bromine, they have the same electronegativity. All right, but if we have 2 separate types of atoms, their electronegativities are a little different. And remember, electronegativity is how hard the atom pulls on the electron. So for instance, I have water here, H2O. In this bond, oxygen has a higher electronegativity than hydrogen. So it pulls the electron pairs that they're sharing closer to it. That means it has more negative than it should, which leaves this side of the molecule slightly negative, which leaves this side of the molecule slightly positive. All right, well, welcome. So what we say is this is a two-sided molecule, a minus and a plus, or we say it is polar. Polar means two-sided. All right. Because of this, when covalent bonds form between different atoms, one of the atoms more strongly attracts the valence electrons of the other atom. That is the one that has a higher electronegativity than the other. It's kind of like you're in a wrestling match, and this is the one that has more weight. It's stronger. All right, this unequal sharing of electrons causes one atom to be more negatively charged and the other more positively charged, resulting in a polar bond. And remember, polar means two-sided. It's like saying top and bottom. Those are two sides, north and south, two sides. Pole, North Pole, South Pole, two sides. So in this example up here, this cloud is representing the probable location of the electrons. And so if the electrons are always around the green, this one is the more electronegative, and this side of this molecule becomes a little bit more negative, and this side becomes a little bit more positive. So we'd say, once again, since it's two-sided, it must be a polar substance. All right, water, we should know, is polar. The polarity of water is what gives it some of its properties and leads to one other thing we're going to talk about later, which is called hydrogen bonds. All right, Amanda is my sister. How cool is that? Tom is my name. I know that's weird. What's that? I have a name. I know teachers are weird. This cloud represents how equally we shared a car when she was a senior and I was a sophomore. We shared a car. Do you think we shared it equally? Not a chance in the world. There are 180 school days in a school year. I will subtract from this number the number of times I got the car. So it was a 1 to 179 relationship. Did we share the car equally? No. In fact, the only person in the world that felt like we shared a car was my mom. She's like, yeah, you guys share that car. I'm like, Mom, this isn't sharing. This is larceny. She's stolen the vehicle from me. It should be 90 to 90 if we're sharing, right? So I would say my sister and I had a polar relationship when it came to sharing the car. So if the fuzziness is representing where the car was, tell your partner which one of these circles represents me and which one represents my sister. Thank you. All right, I'm here, Amanda's here. If this was actual chemistry, which one of those atoms would be the more electronegative one? All right, this would be the high electronegative, this would be the low. So we would sort of say that Tom is a loser. Oh, too soon. Anyway, 1 minute or less. This day, by the way, that I took the car, I just took it. I didn't ask, I took it. And I made a fatal mistake that day. Not fatal, that sounds bad. I made a large mistake that day. I slept school that day to go skiing, which big deal. I did that all the time. But the mistake I made is I went skiing with her boyfriend. All right. And she wasn't invited. She sucked at skiing. So how do you think she felt about that? She's a little mad. So she was a little bit of a conniver back in the day. She knew where I was with her boyfriend, but she called my mom, said, "Hey, I was looking for Tom and he's not here. Neither's the car. I'm worried about him." So my mom called the school because she just figured I parked at a different spot, which was, I did. I parked at Alta. My bad. I didn't realize that I went the wrong way on accident. Anyway, the school tries to find me. They can't find me. I get home at like 5:30. My mom's still at work. I call her up. She's like, "How was school?" Like, "It was good." She's like, "Tell me." So I just made up a bunch of lies. And my mom knew the whole time I was never at school. And then she's like, "Oh, so you were at school today?" And then I knew it was over. And I got in a ton of trouble. So anyway, yay, Amanda, love her. Not bitter. I enjoyed those 48 hours of community service I got for all those U's. Isn't she sweet? Okay, moving on. Polar relationship. You share, but you don't share equal. Get over here, young man. All right. Oh, all right. We okay with that so far? You share, but not equally. That's a polar relationship. Okay, I have another example here. This is from my very own house. Can you tell your partner how this picture illustrates a polar bond or polar marriage? Ready, set, go. Uh, uh, um, okay, any ideas how this represents? And boys, get ready for this because this is life. Okay, so my wife and I, we share this bathroom. Let me show you where all of my stuff is in this picture. It's right here. Huh. I mean, like, I wash my hands with this soap. And that's it. So let me circle all of her stuff here. I mean, I use mouthwash, lotion in the wintertime. So I guess sort of. But the whole idea here is we are sharing this counter space, but we're not really. I'm allowed this back part that wasn't even supposed to be a shelf, but I made it into a shelf because I needed space. But in reality, this is pretty much all I need. I mean, and soap and lotion and mouthwash and whatever. But anyway, we good? Polar. We share, but we don't share equally. The most common thing, once again, in your life that you've heard is polar is water. They are sharing a pair of electrons, but oxygen needs way more counter space than hydrogen does. So it takes the electrons much closer to it. Once again, leaving this half of the molecule negative and these ends of the molecule positive. Now, this negative and this positive are not like an ionic charge. They are called a partial charge. If you've had Bert, it's called the snakety, I believe. It looks like this. That's not very good. It looks like that. All right, so it's a sigma plus. This one needed a curve here. I'm not very good at writing it. And a sigma minus. Ooh, that one's actually pretty close to what it's supposed to look like. So polar, two sides, a negative and a positive. Okay, that was cute. Polar bonds have electronegativity differences of 0.6 or greater and less than 1.7. That is on your periodic table. We okay with that? It's the middle one. Okay, the rest of these are actually pretty boring, so we go quick. Nonpolar bonds, they have electronegativity differences between, sorry, not between. Oh yeah, between the atoms that are less than 0.6. So since these electronegativity differences are close, they share much more equally. So if you're at a tug of war and you're pulling against your exact twin, who's going to win? I don't know. You're both the same size, same strength. You may go on forever because you're going to pull with the same effort. That's what your twin just said. Okay. You have more heart. All right. Because the difference is so small, the electron attractive forces of each atom are almost equal. This results in a molecule with a relatively neutral charge. And this is what makes them kind of boring. Since they don't have charges, they don't interact a ton, and we don't use them a ton in chemistry. They're just not entertaining. So a picture would look like this. They end up sharing the electron equally between them. So there's no partial positive, no negative, and they just do what they do. For you, the most common, probably nonpolar substance that you're used to is gasoline that you put in your car. Then fats like grease. What else would be common? Like the board marker, that ink, it's a nonpolar substances and whatever, oils, all sorts of things like that. All right. Now, I think, thank you, my friend. Right here in the bottom right-hand corner of your front cover, you may have some white space. Front cover, front cover. I may have asked you to write things there before, have I? Okay, perfect. On the front cover, we're going to summarize the 4 types of bonds. Wow, I haven't even done metallic yet, but we can do it because I already made you turn there. This is out of order, but just go with me. We can do it together. All right, let's go this cute color right here. All right, uh-oh. Guess who just texted me? My sister. I hear you talking about me. See, Amanda Hammonds right there. Okay, hold on. Yeah, she's like, where are the keys? No, she's talking about getting a gift for my father. And my mom, I guess, now that I read it. That's just ironic. Okay, so this is just, it's not a flow chart, it's just a diagram. We have bonds, and there's 4 types, even though really this looks like maybe 3. There are ionic bonds, and ionic bonds, these are the things you need to know for sure. They do not share electrons. I don't know why that's written twice. Hold on, did I write a different one? Okay, we're going to go with this one. There is a large electronegativity difference. All right, you're going to add more here. Bond between cation and anion. Okay, super important, they do not share electrons. That's because of their large electronegativity differences that it's a bond between the cation and the anion. All right, Colby, we're drawing this on the front cover, bottom right. Okay, the cover, so like close it right there. All right, then our next main type is covalent, but really it has 2 types inside it. We have polar covalent. They share, but it's unequal. They have medium electronegativity differences. Right, and then you don't have to draw this picture because it's ugly, but if you just put water is polar, that's good enough. I'm going to add that, but you don't have to. Polar means 2-sided. Okay, then we have our non-polar. They're the boring ones. They share equally. they have small electronegativity differences. And then this picture right here is just trying to illustrate the electrons are shared equally between them. And then like put oil is nonpolar. So like your, when you make Italian dressing and it doesn't mix, it's because it's made out of water. That's the stuff that carries all the flavoring. It's dissolved in water, and that's a polar substance. But then it has oils on it to give it that little extra greasy flavor that we, not all of us, but a lot of people like. And you like shake them and they blend together, but they don't really like mix into one thing. So that's why they'll separate. Okay, then metallic bonds, which we'll talk about with like 2 slides. A metallic bond, just remember, it's a sea of electrons. That will help you get both answers right. And in the notes in a minute, I'll actually talk through those. Okay, so fill that in real fast. Now, there's a lot of test questions that come from just this slide. When you look at your competencies, and it just says like general bonded questions or something like that on the front, what does it say? Bonded concepts. A lot of them are from here. Okay, I'm going to move on about 30 seconds. If you're not done, you can take a picture of it and finish it. I need to wrap up metallic. There is another type of bond, sort of, that we're going to talk about. I don't have it on here because it's actually not a real type of bond. In chemistry, it's annoying that they even call it a bond because it's not. All right, so I'm going to move on. And here we go, metallic bonds. So this really should have been after these 2 slides. I apologize for all the page flipping. How many? 2? Okay. A metallic bond is when we're talking about what keeps a piece of metal together. So like if you look at the legs on your desk, they're shiny. We know they're metal because we're used to just the properties of metals and looking at them. All right, the bonds in those pieces of metal are called metallic bonds. So in a pure piece of metal, the valence electrons are free floating among closely packed, positively charged ions. All right, the sea of floating electrons are what gives metals their physical properties. All right, that literally is it. Then there's this picture. So in a metallic bond, you have the nucleuses. That's a rough color to choose, but whatever. And then you have all these electrons that are just cruising around wherever they feel like. This is like a game of musical chairs where the music never stops. So if the music never stops in musical chairs, does it matter how many chairs we have? No. And in a metal, all of them don't want their valence electrons. So it's like they let them all run around and pay no attention to them. This would be, and sounds rude, but it's my neighborhood right now in the summer. There's like 20 kids, and like we like them, but they need to be out of the house a lot. It's probably your house. All right, so you just kind of let the kids go and you assume that they'll stay inside the neighborhood. And if there's a problem, some mom at some point in time could save that, whether it's, you know, the Thompsons or the Pecks or the Davidsons. I'll put an honorary face for me. Or whatever. All the parents both take care of none of the kids and all the kids at the same time. That kind of makes sense. It's just, I'm sure there's neighborhood after neighborhood that's kind of like this. The metallic bonds the same way. The parents, that would be the nucleus, let the electrons go wherever they want because at any given point in time, they have all they want and none of them that they want. Okay, the matching term and multiple choice, look for the word C. And remember that the C in the song is C to shining C. And what things are shining? Metals. C to shining metallic C. Okay, moving on. The last thing to talk about is hydrogen bonds, which this is really a pet peeve of Tom Davidson. They are actually not bonds, but I didn't get to name them. So just stick with them. They're called hydrogen bonds, which are actually attractive forces in which hydrogen that is covalently bonded to a very electronegative atom is also weakly bonded to an unshared electron pair. So this is why it bugs a lot of chemistry teachers that they call it a bond. So this is not exactly right, but these are magnets, right? A bond would be the thing that keeps the magnet together itself. A hydrogen bond is like the attraction between the two molecules. Like I can pull that apart because it's not bonded, it's just attracted. I can pull that apart. It takes some effort, but it would take a gigantic amount of effort for my fingers to pull the bonds apart in the actual magnet. Okay, so a hydrogen bond, it's called an intermolecular force. It's an attraction between two atoms, or sorry, molecules that have hydrogen in them and an unshared pair of electrons. So if you look right here, we know water's polar, which means that the oxygen is slightly positive, or sorry, slightly negative. I was looking at that plus. It's slightly negative. Hydrogen was left slightly positive. And so since it's sort of positive and oxygen's a little bit negative, they will attract to each other like two magnets attract. So that is called the hydrogen bond, when hydrogen is attracted to the unshared pair of electrons on oxygen. Okay, but it does not form a real rigid bond. It's why water like comes out as a stream. All right, so water sticks together because it's all attracted to itself. All right, has anyone ever tried to pour paint thinner out of a metal can? It's the worst thing ever. I don't know who designed that metal can, but paint thinner doesn't attract to itself, it attracts to the can. So you pretend this is the can and here's the opening and here's your thing you're gonna pour it into. You go real slow because you know paint thinner is like gross and whatever, and it comes off of here. You're like, what? Water doesn't do that. Water comes out and sticks all together. Well, the gasoline, paint thinner, whatever, it's more attracted to the metal than it is itself. And so really you got to go slow and put the cup here, which makes no sense. But in chemistry you do, or it does. It's called an intermolecular force. So hydrogen bonds are really attractive forces between two independent molecules that have other types of bonds. All right. Ooh, that's the end of our bonding, isn't it? Whoo-wee. All right. What? Non-polar? That was like 2 years ago. Right here? Is that what you need? Okay. Now, I have one of the greatest things ever created for you now. Now, when you look at it, you may not think it's as awesome as I know it is, but just trust me. Take some of these and just pass them that way. You're the best. Our test is next Friday. Probably every test in every class is going to be next Friday. They told us yesterday to not test on the Monday or Tuesday before Christmas. There's kind of an idea that we won't have normal school those 2 days. Yep. Oh, man. Well, you're welcome. I'm coming. I will show you here in a second. Did everyone get one? All right. This piece of paper is as valuable as your periodic table. You get to use it on the test. And what it helps you do is really difficult unless you have this. Did everyone get one? Okay, you're going to fold it so that where it says polyatomic ions, that's the front page. So common polyatomic ions, that's your front page. All right. Why is my throat so dumb? I am not tonight, actually. Mr. Parker, were you going to do something? No. Oh. Oh. Tonight is a party that I have to go to. But I'll be there tomorrow for the girls' game. Yeah. Which is new to the schedule. I don't know if Cheer even knows about it. Okay. So everyone look, it says common polyatomic ions on the front. Turn it to just the back. So don't open it, just look at the back. And it says, use this side to find the formula. Is everybody with me? Okay, today, for the next 15, 20 minutes, we're going to use the side that says common polyatomic ions and the back, which says use this side to find the formula. Now, I thought I had this open already. Let me find it again. All right. So take your lab book and just turn it to the back. Just go to the very back, just shut it. And you'll see 50 problems. Today, we're going to start on those. We're going to start on the side that has names, and we're going to try and find their formulas. Okay, don't move. All right. So look back at this side real quick of the naming schemata. Okay, so just an introduction to what polyatomic ions are. We know that ions means it's charged, correct? So that's that part. Next, it says polyatomic. Poly means more than one atom that has a charge. So if you look right here, this combination of C2H3O2, it has one extra electron to make it work. It is an ion. Now, ions don't exist by themselves. They always exist with a metal. So this thing, and don't write on here, but this got one from like sodium. Sodium had its dot, it gave it to this thing called acetate, and now it exists as an ion, and we would write the formula NaC2H3O2 and call it sodium acetate. Okay, so these are ions with more than one type of atom in them. All of these are -1s, all of these are -2, and all of these are -3. Will you put a box around this one right here? That one is unique in that it is the only one that's a positive polyatomic ion. Every other one that we do is a negative. So when we write formulas, if we ever have NH4, we'll start the name with it or the formula with it. This is on the left. The plus is always on the left. The minus is always on the right. So this is the only one where it's the first thing we write. All of these would be the second thing we write. Okay, so let's dive in here. Now look at this side. I know yours isn't colored, but it doesn't need to be. And let me double check that I have the right one. 50. Uh-oh, I don't. Okay, well, I guess open it up to, and then we'll look at the top right side. I'm sorry. Open the lab book up and look at the top right side, not the naming schemata. We're going to be on the back of the naming schemata. But we're going to be on number 51, which is inside right here. Everyone with me? Everyone with me? 51, 51, 51. We're going to be here. And we're going to be here. Okay. So what the naming schemata is it's a giant table with a million questions and then a little bit of directions. So we're going to ask ourselves these questions about 51, which is potassium chloride. I start right here. Is potassium chloride the name of a single element? The answer is no, or it would just say potassium. All right, so I come down here. Does this word end with the word acid? No. If it did, it would say acid. Are there metals and non-metals? Well, that's tricky. You got to really know those now. Staircase. We have one from here and one from here. So what's the answer? Yes. Does the ending, this box is always asking about how it ends, like right here. Is the ending ATE, ITE, hydroxide, cyanide, or peroxide? No, it's just plain IDE. So this tells me the directions. Give the symbol of the metal first and the non-metal second. So we're not done, but it just says put the symbol, which is K, and then the non-metal second, which is Cl. Then this piece right here is really important. You got to do it every time. Balance the plus and minus charges by using subscripts. Or what I would have you write, like right here, I'd put drop and swap. Drop and swap. So, do we remember what drop and swap was? Okay, well, thank you for saying no. Let's review what it is. Oh, well, it doesn't matter on this one. That's true, but it will eventually. Potassium is in family 1, so I put a +1 above it. So you'll need your periodic table as well. Chloride is a -1, and then we would drop and swap them. So +1, -1, I would drop, but they're both 1s. So if they're both 1s, do I need to put anything? No. Gabby, wouldn't have this have been nice in regular or AP? Yeah. In AP chemistry, they just have to memorize every rule and figure it out. It's really hard. Okay, so 51 is just plain KCl. Now look, let's pretend this was a 3. Then it would have been K3Cl. We drop them and then we swap them. Okay, let's look at 52. Lithium oxide. So same thing. It is not the name of a single element. Does it end with the word acid? No. Are there metal and non-metals? Yes, there are. It does not end with any of those. So we're in the same box again. I'm going to put it here because it's just a lot more room. List the symbol of the metal first. That's Li. Oxide, that is oxygen. So I put an O second. And then I drop and swap. Have your periodic table handy. We put those numbers up there a while ago to help us, right? So tell your partner the charge of Li. Yeah. No. That has bolts in it. You know how they're like compacting that place out there? They're making that parking lot and it vibrates my room when they compact, and it just swung down the other day. Seriously? It's kind of freaky. Yeah. Okay, so thumbs up if you know where to find the charge of lithium. Right here. It's a +1. Charge of oxygen -2. Drop, swap. Li2O would be the answer right here. Easy enough? Okay. Sodium, I'm going to go to one that takes us to a different box. All of these go to the same box. So let's go to 55. Like, you'll still need to do the other ones, but 55 takes us to a different box. So we're looking at carbonic acid. Is that the name of a single element? No. Does it end with the word acid? Yes. Okay, make sure you're watching here. Write the formula of the acid by using the chart. The chart is actually in the big middle part. So open it up, and then it's right here. And you don't have to memorize these. Gabby's probably mad again because acids were a pain in the acid. They were way hard. They're all right there. So it just tells you the formula of carbonic acid is what? H2CO3. Okay. Let's look at 57. 57 is different but similar. It has Roman numerals in the middle, so it's kind of a little bit like, what? So it says copper 2 oxide. So to save time, we're just going to end up straight down here again. So you're like, well, we've already done those. How is that different? The difference is this. Please make sure you listen to this part. That's just the charge of the metal. So when it says give the symbol of the metal first, the non-metal second, then it says balance the plus and minus charges by using subscripts. If you look on your periodic table, you will not find a charge for Cu because transition metals charges can be variable. The Roman numeral always tells you the charge of the previous metal. So there's a +2, there's a +3, there's a +2, there's a +2, there's a +3. It always tells you the charge of the metal. Now, how did I know it was a plus besides I'm obviously a genius? It's a metal, and metals are losers. Okay, so here we go. 57 copper 2 oxide. So we have Cu and O. The Roman numeral tells me copper is a +2. Oxygen is on my periodic table. Tell your partner what its charge is. -2. Do I put anything down here? Nope, I call that good. Okay, you guys are great.